Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, we're asked to figure out several characteristics of an alpha particle that is going to be accelerated through a potential difference and then travel through a magnetic field completely perpendicularly. And we know when that happens, the particle is going to follow our circular motion that we've studied previously, and that we know how to define the radius of that motion. So let's just think about the situation here and then solve for what we need to. So initially, we are asked to solve for the speed of the alpha particle. Well, this alpha particle is going to be accelerated through a potential difference from some higher potential to some lower potential of a particular value. I think in this case it is 1.2 times 10 to the 6 volts. What happens here, right, is we have our charge, Q, and that's going to be a plus 2e because it's an alpha particle. It's going to start at some initial velocity here of 0, travel through this potential difference, and then when it gets here, is going to be traveling at set new final velocity vf. Just some new final velocity that it's accelerated up to. Let me rewrite that better. Okay, so the first question, part A, is asking us how fast is this particle going to be traveling? Well, we have to go back and think about accelerating through potential differences from previous chapters. But we know that when this charge goes through this potential drop, is going to lose an amount of potential energy given by the value of the charge multiplied by that potential drop. But that loss of potential energy is going to be a gain in kinetic energy of our particle, and that equals a 1/2 mv squared, v final squared technically, minus 1/2 mv initial squared. But our initial velocity is 0. So if we want to find that final velocity, we just have to figure out what our loss of potential energy is. And we know that because we know the charge of our particle and the potential drop that it goes through. So let's write this expression here and then solve. So we have an equation equating our potential energy loss to our kinetic energy gain. And then I just want to solve for my final velocity because I want to know how fast my particle is going to be traveling through that magnetic field so I can tell things about the magnetic force on that particle. So solving for this, we see that we get the square root of twice the charge of our particle multiplied by the potential drop, all divided by the mass of our particle. So if I plug all these things in, let's see, I get the square root of 2 times twice the fundamental charge, 1.6 times 10 to the negative 19 coulombs, and that's going to all be multiplied in the numerator by our 1.2 times 10 to the 6 volts. Then, of course, we're all going to divide this here, this is a C, divide this here by our mass of a alpha particle, which is given to us as 6.64 times 10 to the negative 27 kilograms. Put all this in our calculator, and we see for part A, we have a final answer that the speed of this particle is about 1.08 times 10 to the 7 meters per second. So again, pretty quick, but not quite enough to have us have to think about relativity. Now that we know the speed of this particle, it's rather easy to find out part B and part C. So we're really just going to plug in numbers into our equations. So for part B, we want to know the magnitude of the magnetic force that this particle is going to feel, and that means we just need to look at our magnitude of the magnetic force equation, which means we multiply the charge of our particle by its speed, multiply it by the magnitude of the magnetic field through which it is traveling, and then multiply that by the sign of the angle between our velocity vector and magnetic field vectors. Now, we have a charge of 2e for our particle here. We just figured out how fast it was going. I believe we are given the magnetic field magnitude through which it is traveling, and we're told that the magnetic field and the velocity are always perpendicular, and therefore we have a sine of 90, and that goes to 1. So we just have to then plug in all the numbers that we know. So 2 times the elementary charge, 1.6 times 10 to the negative 19 coulombs. Multiply this by the speed we found just up top here, 1.08 times 10 to the 7 meters per second. Let me do a little dividing line between our work here so we don't get confused. And then we're going to, again, finish this equation off by multiplying by the magnitude of the magnetic field through which it's traveling, which is 2.2 Teslas. We pull all this into our calculator, and we see that the magnitude of the magnetic force that this alpha particle is feeling is going to be 7.60 times 10 to the negative 12 newtons. Okay, and for part C, let me clear this off. Part C, we just want to know what is the radius of the circular path that this particle travels through. And again, we know the equation for this, and we know everything we need to. The radius of the path that a particle is going to travel through in a uniform magnetic field is given by its mass times velocity divided by its charge and the magnetic field magnitude through which it is traveling. And we know all of this information. So we just plug in what we know. Mass of our alpha particle, how fast our alpha particle is traveling in this magnetic field. Divide that by the elementary charge, which again is the charge of the alpha particle, which is the elementary charge, multiplied by 2. And then again, the magnitude of the magnetic field is 2.2 Teslas. Throw that in our calculator, and we get our final part C answer. Let me write that here, is 0.102 meters. And that is the end of our problem.